Welcome to The Deep Dive, the show where we cut through the noise to get you the essential knowledge you need. And today we're doing something really specific, aimed right at you if you're gearing up for a major qualification. We're diving into our CSWIP 3.1 exam prep series. This is all about helping you prepare for that welding inspector exam. We'll tackle some multiple choice questions, but, not just finding the answer. We want to get into the why, give you that shortcut to really understanding it.
Exactly. Because that true understanding, that's what really counts. It goes way beyond just memorizing for the exam. It's about being competent, out there in the field. That's what we're aiming for here. A solid grasp of the principles. We'll take our time, unpack things clearly.
Okay, sounds good. Let's start with something fundamental then. The document that kind of orchestrates everything. Let's get straight into the first question. A qualified welding procedure specification, or WPS, is used to. Is it A, give instruction to the welder, B, give information to the welding inspector, C, give confidence that welds will have the specified properties, or D, all of the above? Okay, take a second. Think about how broad the role of a WPS really is.
Right, it touches on so many aspects of the job. And the answer, the one that really pulls it all together, is D, all of the above.
All of the above, okay.
Yeah, it really is that central document. It's not just one thing. Think about it first for the welder. It's their detailed instruction manual, step by step. It tells them everything: materials, settings, speed, preheat, everything needed for consistency. You avoid guesswork.
Right, consistency is key. And for the inspector?
Well, for the inspector, it's the benchmark. It's the standard they inspect against. It lays out exactly what to check, what the acceptance criteria are, makes their job objective, clear.
Okay, so instructions for the welder, benchmark for the inspector. What about C, the confidence part?
That's maybe the most crucial part. A qualified WPS. The qualification means it's been tested. Rigorous tests have proven that if you follow this procedure, the weld will have the right properties, the strength, the toughness, whatever is needed. It's documented proof. It gives everyone confidence in the final product's integrity.
So it really ties the whole process together. Design, execution, verification, all linked by the WPS.
Absolutely, it's the bedrock.
What happens when it goes wrong? When people don't follow it or maybe don't understand it properly?
Oh, the consequences can be really severe. Imagine skipping preheat on a critical joint because someone didn't check the WPS. You could end up with hydrogen cracking, which, well, we'll probably get into later. That can lead to failure.
Catastrophic failure.
Potentially, yes. Or an inspector might miss something crucial, accept a bad weld, or reject a good one, causing delays and costs. Ignoring the WPS can lead to failures, rework, massive delays, even legal issues. It undermines the whole project's safety and economics.
Okay, that really drives home its importance. Let's move from the how, defined by the WPS, to the physical effects of welding, specifically distortion, that warping and twisting that can happen. So the next question is, the property of a material which has the greatest influence on welding distortion is it A, yield strength, B, coefficient of thermal expansion, C, elastic modulus, or D, coefficient of thermal conductivity? Think about that intense localized heat. What physical property matters most when things start to bend out of shape?
This is a really core concept. The answer is B, coefficient of thermal expansion.
Coefficient of thermal expansion, okay.
Let's break that down. Distortion basically is the metal changing shape because of the welding heat.
Yeah.
You heat a small area very hot, it wants to expand, then it cools and wants to contract. But the surrounding metal, which isn't as hot, resists that expansion and contraction. This creates internal stresses.
It's like the metal is fighting itself.
Exactly. And the coefficient of thermal expansion tells you how much a material tries to expand or contract for a given temperature change. A higher coefficient means more expansion, more contraction, stronger internal fight, and therefore a greater tendency to distort. It's the primary driver.
So what about the other options like thermal conductivity? Doesn't that play a role?
It does play a role, absolutely. Thermal conductivity affects how quickly heat spreads, so it influences the size of the heated zone and the temperature gradients. But it doesn't directly dictate how much the material expands or contracts for each degree change. That's the coefficient of thermal expansion. Yield strength matters because if the stresses exceed it, you get permanent deformation. But the amount of expansion driving those stresses comes from the coefficient.
Got it. So conductivity affects the heat pattern, yield strength affects whether it bends permanently, but the expansion coefficient is the main engine driving the whole distortion process.
You've nailed it. That's the fundamental mechanism. High expansion coefficient equals higher distortion risk.
Makes sense. Okay, let's shift gears to consumables, specifically electrodes. There's a crucial prep step for some types. Next question. A typical temperature range for baking basic coated electrodes is A, 150-200 degrees CAB, 200-250 degrees C, 300-350 degrees C, or D, 400-450 degrees C. Why do we bake these, and what's that magic temperature range?
Right. This is super practical, something inspectors check all the time. The correct range is C, 300-350 degrees Cs.
300-350 Celsius. Why so specific and why so hot?
Okay, so basic coated electrodes, they give you really high quality welds, good toughness, often used for critical stuff, but their coatings are hygroscopic.
Meaning they suck up moisture.
Like a sponge, yeah. They just pull moisture right out of the air. And moisture, H2O, contains hydrogen. Hydrogen is the enemy here. If it gets into the molten weld pool from the electrode coating,
It causes problems.
big problems. It can lead to hydrogen cracking, also called cold fracking. It's a delayed crack, can happen hours, even days later.
Yeah.
Very dangerous.
Because the weld looks fine initially.
Exactly. It looks perfectly good, then suddenly fails. So baking is essential to drive out that moisture, to remove the hydrogen source. And that specific range, 300 and 350 degrees C, is critical. You need it hot enough to effectively remove the moisture, but not so hot that you damage the flux coating itself.
So too cool, you leave moisture in. Too hot, you wreck the electrode coating.
Precisely. You have to hit that sweet spot. I've seen failures directly linked to improper baking or handling after baking. It's not a trivial step.
That's a really vital, practical point. It connects the theory of hydrogen embrittlement directly to a simple workshop action.
Absolutely. Attention to detail prevents defects.
All right, let's move from preventing defects to understanding failures when they do happen. Let's talk about fracture surfaces. When you look closely at how something broke, the surface tells a story. So the question is, the surface of a fatigue crack will A, be rough and torn, B, have sharp chevron markings, C, be smooth, or D, have shear lips. How does a crack that grows slowly over time under cyclic load look different from other breaks?
This is fascinating stuff like material forensics. The answer is C, be smooth.
Smooth, why is that?
Well, remember what fatigue is. It's not one sudden break. It's a crack growing bit by bit, cycle after cycle, under repeated stress. Think of bending a wire back and forth. Each bend extends the crack a tiny amount. As the crack grows, the two opposing faces rub against each other slightly as the load cycles on and off. This repeated rubbing action polishes the surfaces, making them appear relatively smooth, sometimes almost shiny.
Polished by the failure process itself.
Exactly. You might also see patterns called beach marks or striations on that smooth surface, which show how the crack front advanced over time. Very distinctive.
And the other options, rough and torn, chevrons.
Those are usually signs of different failure modes. Rough and torn often indicates a ductile overload failure, lots of plastic deformation. Sharp chevron markings typically point towards the origin of a brittle fracture, a very rapid crack propagation. Shear lips also suggest ductility, but that smooth, possibly beach-marked surface, that screams fatigue.
It really is like reading the material's history, a vital skill for an inspector investigating a failure.
Absolutely. The fracture face holds the clues.
Okay, final question for this deep dive. Let's circle back to hydrogen cracking, but this time focus on the material itself. The risk of hydrogen cracking is greater when MMA welding, A, CMN steels, carbon manganese steels, B, austenitic stainless steel, C, low alloy steels for elevated temperature service, or D, low carbon steels for cryogenical service. So which of these materials is inherently more vulnerable to this type of cracking?
This ties together material science and practical welding risks. The highest risk among these options is with C, low alloy steels for elevated temperature surface.
Okay, why those specifically?
All right, let's quickly recap. Hydrogen cracking needs hydrogen, stress, a susceptible microstructure, and low enough temperature. Low alloy steels designed for high temp service, think power plants. Refineries are often higher strength. They get that strength partly from alloying elements and sometimes heat treatment. This means their chemistry, their higher carbon equivalent, makes them much more likely to form hard, brittle microstructures like martensite when they cool after welding.
And martensite is particularly bad for hydrogen cracking.
Extremely susceptible. It's hard, brittle, and hydrogen can embrittle it very effectively. So these steels inherently tend to form that susceptible microstructure more readily than the others listed. That's why they often need significant preheating to slow the cooling and avoid forming martensite and super strict hydrogen control. The risk is just inherently higher.
And the other steels, why are they less risky in this context?
Well, CMN steels are generally lower strength, less alloyed, less likely to form lots of martensite. Austenitic stainless steels have a different crystal structure, kind of more forgiving to hydrogen in terms of cracking, though they have other welding issues. And low-carbon cryogenic steels are designed for toughness at low temps. Their metallurgy generally doesn't lead to the same high hardenability risk.
So it really comes down to the specific metallurgy and how likely it is to form those brittle, hydrogen-susceptible phases during cooling.
Exactly. Material selection dictates the level of precaution needed. It's not a one-size-fits-all situation.
That's a perfect example of how deep the inspector's knowledge needs to go. Understanding the material science is crucial. And that brings us towards the end of this deep dive. Wow, we covered some ground. We looked at the absolute centrality of the WPS, how it guides everyone. We nailed down the coefficient of thermal expansion as the key driver for distortion. We covered the vital importance and the specific temperature for baking basic electrodes to fight hydrogen. We learned to spot the telltale smooth surface of a fatigue crack. And just now, we identified why certain low alloy steels pose a higher intrinsic risk for hydrogen cracking. Going through these questions, really unpacking the why, hopefully helps solidify this knowledge for your CSWIP 3.1 exam prep.
Definitely. Building that foundational understanding is key. And maybe a final thought to leave you with. As you reflect on these points, the WPS, distortion, baking, fatigue, material susceptibility, consider how they all interlink. How does getting each part right contribute to the overall safety and reliability of a welded structure? And maybe more importantly, what are the potential ripple effects, the unseen consequences, if just one of these critical elements is missed or managed poorly in practice?
That's a great question to ponder. It really emphasizes the holistic nature of welding quality. Thank you so much for joining us on this deep dive. Keep studying, stay curious, and we look forward to diving deep with you again soon.